to really conquer, in general, more and more domains, we have to have something other than wheeled robots. And something that we know works is legged locomotion, right? We use it. Most of us use it. And legged robots are not yet at the same level of maturity. But, again, tremendous progress is being made every day. Here's an example from a company called Boston Dynamics, which is now part of Google. And this is one of the first legged robots that they successfully demonstrated. This is Big Dog. It's a quadruped. And it was one of the early robots that was shown able to robustly navigate difficult, unknown terrains. So this forest floor is a pretty difficult terrain, all kinds of obstacles, and then, changes in how slippery the ground is. Maybe you step on a branch that rolls away. Maybe you step on a sheet of ice. This is an example of the robot handling disturbances. Here's another example. This is the robot slipping on ice. And it may look wobbly. Actually, this is incredibly impressive how it's able to recover. Think about how dramatic a surprise this robot encounters. It's stepping on asphalt, nice, solid, with high friction coefficient, and then all of a sudden it steps on ice, incredibly slippery. And still, even though it's faced with this massive, dramatic change, unexpected change in the environment, it doesn't have the sensors to look at the scene and know that there's ice ahead. It only knows about that patch of ice once it steps on it and the foot just doesn't stick. Most of us, I think, when that happens, we would fall. Big Dog, in this example, recovers, right? And then here are more examples from the same company who then proceeded from quadruped locomotion to biped locomotion. This is an example of one of their more recent example, one of the smaller bipeds. And here, notice it moving around, opening doors. Now you get a sense, hey, this could really go into a human environment. But not walking just down a nice corridor, carpeted corridor, again, able to go outside, handle what is really, truly very difficult terrain in robotics, uneven. You never really know when you step on a patch of snow how deep your foot is going to sink. And still, this robot is able to navigate this incredibly difficult, complex terrain. Right? Anyway, this robot doesn't, again, have the background knowledge that we have in terms of how snow operates, how likely a patch of snow is going to be deep or shallow, depending on how it looks. And here it is, able to do not just move itself around, but also start picking up external items from the environment. Here's another example of that, also from Boston Dynamics, a very nice blend of wheeled and legged locomotion. And really, what the field is working on here is this ability to really understand balance from a dynamic perspective, and to really be able to maintain equilibrium under all kinds of very significant dynamic disturbances. And once you have a really deep understanding of that problem, then walking or this kind of very impressive legged driving, they become particular instances of it that you know how to solve. Again, disturbances that the robot maybe doesn't know about in advance, and it's still able to handle them appropriately. And then another example of legged locomotion, maybe these robots, while extremely impressive from a robotics perspective, they still don't look as sure-footed as a human, as a person. The field is getting there. But there are places where robots can exceed human capabilities in some dimensions. And here is a robot in a research lab from MIT. The Cheetah is an incredibly fast legged robot, and here they are demonstrating it being able to not just run faster than most humans, but also to jump over obstacles. And the interesting thing, again, the obstacles are not known in advance. So the robot uses its sensors, and in particular a laser range sensor, to see the obstacle and then to plan its footsteps to give it a possible jump over the incoming obstacle. And the obstacles get bigger and bigger. Okay. So legged robots, maybe they are not deployed today, or maybe they're not as close to deployment as wheeled robots, but are making progress in leaps and bounds, if you wish. Putting this all together, mobility, manipulation, wheeled locomotion, legged locomotion, here's an example of a complete scenario where a robot is meant to go through a number of tasks inspired by disaster response application. So here is a robot that recently won this robotics challenge that is going through a number of tasks. First, it opened the valve, then what's doing, it's picking up a drill. Notice that in this particular case, it's driving around in wheeled fashion. So it picked up a drill, now it's actually drilling a hole in a wall. And this is a robot capable of legged locomotion as well as wheel locomotion. And why not, right? This is not something that we are able to do, but hey, it's fair game, right? So when needed, it can get up and walk, but when the terrain is nice and flat, why not take advantage of the possibility of wheel locomotion and drive around? If you can power through obstacles rather than gingerly stepping through them, even better. You get to somewhere where wheels really don't work anymore, then you get up and you walk if you can. This also gives you a sense how much the video is sped up. This is a particularly difficult task. And again, this is nice because it combines multiple forms of locomotion. You're not bound to just one when designing a robot. There are other types of robotic mobility, not just these. Aerial robots. And I'm sure that if I say aerial robots, the first thing you think about is quadrotors. But what I want to show here is that that's not necessarily the only type of aerial mobility. This is Project Wing from Google X, and this is showing as an application delivering items to a remote part of Australia. And this is actually fixed wing robotic aircraft that's able to traverse large distances. It's fast. It can localize itself. It knows where it is. It knows where it needs to go. So then what it does is it can traverse large distances quickly and deliver its payload to where it needs to go. So this is an example of the payload. It's just dropping the payload to its destination. Right? So more surprising types of robot mobility. Underwater robots as well. The list continues. Right? Again, this is not exhaustive by any means. It's just meant to show, hey, here, these are some commonly known examples. And then finally, just to really drive that point home, manipulators, mobile robots, they are pretty well known and accepted as robots. They either have had an impact on society already or are about to. But really the world of robotics is much, much bigger than that. And there are other things that, again, maybe you don't think of them as robots, but we could, right? So there are things that don't look anything like manipulators or mobile robots. But still, if you think about, this is an example of the learning thermostat from Nest, the company Nest, which is also right now part of Google, right? So what this thermostat does is it regulates the temperature in your house. and it adapts to your habits and reacts appropriately. So is this a robot? And again, we are back in a way at where we started from, right? The dishwasher. And really, the question of how do you define a robot? And now that we've seen a whole bunch of them, can we really come up with a definition? There are many, right? A commonly used definition of a robot is a device that can sense, plan, and act. And this loop between sensing, planning, and acting is considered one of the keystones of robotics. And that's generally a good definition. However, some of the manipulators, the industrial manipulators that are universally accepted as robots, is there a lot of planning going on, especially if a human has pre-programmed the trajectory in advance? A robot, to me, is any self-powered device that effects physical change on the world. And that can mean an arm that's moving things around. That can also mean a robot that's driving itself around. A robot that's driving itself around obviously affects physical change on the world because it's moving itself. It doesn't have to move something else. The dishwasher, it meets my definition, right? It does affect physical change on the world, and it is self-powered. You put in the dishes dirty, you take them out clean, right? That's an obvious example of physical change. And then if you think about it, actually, the dishwasher, it looks like, okay, it meets the second definition, definitely not the first. The dishwasher will have a surprising number of sensors. It will sense, for example, the weight of the dishes that you're putting in. It'll sense the humidity inside. It'll sense the temperature of the water. Some advanced dishwashers will sense how dirty the dishes are. So they will have surprising number of sensors, and they will react appropriately to unforeseen conditions, right? So this kind of shows why there is really no universally accepted definition of what a robot is. To me, the dishwasher is a robot. To you, it might not be, and both answers are correct, right? An incredibly broad field, but the key, again, to me, is this ability to effect physical change on the world. It's a robot once you stop talking about just bits. Bits on a computer, bits on a hard drive. Once you have a physical realization of what you're trying to do in the world, then it becomes a robot. And that, to me, is what makes robotics an incredibly exciting field. Another thing to keep in mind in terms of defining robotics is that we're talking about the software and the hardware. And in robotics, they are really inseparable, right? If you think of them as, the mind and the body, then it becomes clear just how inseparable they are. Just when you think about humans, the mind and the body are completely and utterly tied together. You cannot really imagine, if you take one without the other, you no longer have a human. And it's very similar with robotics. And again, it's part of what makes robotics an exciting field to study, this interrelation between software and hardware.